Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on ARMA modeling. And in this lesson, I'll continue with introducing the concept of ARMA modeling, particularly focusing on introduction of causal and invertible processes. Let's return to the notation of the ARMA process. We write the ARMA model in a more compact form as provided on a slide. That is, we multiply xt with phi of the operator b, representing the left portion of the model equation, and multiply zt with theta of the operator b, representing the right portion of the model equation. The function phi and theta are defined further on the slide. Phi is a polynomial of order p with coefficients given by the AR portion of the model. Theta is a polynomial of order q with coefficients given by the MA portion of the model. The polynomials are called auto-regressive and moving average polynomials, respectively. The operator b is a lag operator. When applied to the time series xt, we move the index back one time unit given xt minus 1. When applied multiple times to xt, for example k times, we move the index back k units giving xt minus k. Here, we establish the necessary and sufficient condition for an ARMA model to have stationary solutions. The question we'll address now is, when xt is stationary given its representation as an ARMA process, or when the ARMA model generates stationary processes. As provided on this slide, the condition only involves the AR polynomial phi, and it says that this polynomial does not have solutions on the unit circle, or that the solutions of the polynomial phi z are not equal to 1 in absolute value. Thus, for checking whether an ARMA process is stationary, we simply need to get the solutions to a polynomial and check whether on the unit circle. Given a time series probability model, usually we can find multiple ways to represent it. Which representation to choose depends on the context of our problem. However, not all ARMA processes can be transformed from one representation to another. In this lesson, we'll consider under what conditions we can invert an AR model to an MA model and invert an MA model to an AR model. The concept of causal process means that we can invert an AR or ARMA process into an MA process where the order can be up to infinity. An ARMA process xt is causal if we can express it as a linear process in zt, which is a white noise, such that the sum of absolute values of the coefficients of the linear process is finite. The simplest example is an MA process of order q. When does an ARMA process is causal? Similar to the property of stationarity, not all ARMA processes are causal. First, we assume that the two polynomials phi and theta do not have any common zeros. That means the solutions to the equation phi z are not equal to the solutions of the polynomial theta z equal to 0. Then a necessary and sufficient condition for the process xt to be causal is that the zeros of the AR polynomial are outside of the unit circle. In other words, if for any z, which is a solution to the equation phi z equal to 0, if any z when the equation phi z is equal to 0, then that z is larger than 1 in absolute value. Note that this condition implies that if a process is causal, it's also stationary, but not the reverse. That is, there are stationary ARMA processes which are not causal. Given the two polynomials of an ARMA process, we can then obtain the coefficient psi of the linear process representation using this relationship, which is an invertibility property of the AR polynomial. This relationship will come handy in the estimation of the ARMA process and in prediction. One simple example for a causal process is the AR of order 1. The polynomial for such process is 1 minus phi z, which equals 0 when z is equal to 1 over phi. Thus, xt is stationary if and only if the solution is not equal to 1, or equivalently, phi is not equal to 1. Moreover, xt is causal if and only if the solution 1 over phi is larger than 1, or equivalently, phi is smaller than 1. Thus, for an AR1 process, it is straightforward to check whether the process is stationary or causal. Here, I simulated AR1 processes with phi equal to 0.1, minus 0.1, 0.9, and minus 0.9. The simulation is similar as the one provided in the previous lesson. We first simulate the white noise, then we apply the filter command with method equal recursive. The time series plots are here. Upper plots are for small phi equal to 0.1 or minus 0.1, and lower plots are for phi close to 1, 0.9 or minus 0.9. The upper time series plots show clear stationarity as there is not a pattern in this time series. On the other hand, the plots on the bottom show some sign of non-stationarity. The departure from the mean zero is very prolonged. This is because the coefficient phi is 0.9 in absolute value, which is close to 1. As pointed out on the previous slide, an error 1 is not stationary when the coefficient is 1 or minus 1. Thus, as the coefficient phi reaches 1 in absolute value, the processes also will show signs of non-stationarity. We can also go from an MA or moving average process or more general ARMA process to an AR process where the order can be infinity, meaning that the ARMA process is invertible. More specifically, for a process to be invertible, there exists constants pi j, where the sum of the absolute value of the constant is finite, such that the linear combination of past xt minus j's weighted by pi j is a white noise zt. A necessary and sufficient condition for an ARMA process to be invertible is that the zeros of the MA polynomial theta z are outside of the unit circle. That is, the solutions to the equation theta z equal to 0 are all larger than 1 in absolute value. Given the two polynomials of an ARMA process, we can then obtain the coefficients pi of the linear representation using this relationship, which is an invertibility property of the MA polynomial. We prefer the invertible ARMA processes in practice because if we can invert an MA process to an AR process, we can find the value of zt, which is not observable, based on all past values of xt, which are observable. If a process is non-invertible, then in order to find the value of zt, we have to know all future values of xt. Here is why the property of causality is important. Given an ARMA process with AR and MA polynomials, phi and theta, if it is stationary, that is, the roots of the phi z polynomial are not on the unit circle, then there exists polynomials pi tilde and theta tilde and a white noise zt tilde, such that the ARMA process with these polynomials as AR polynomial and MA polynomials is a causal ARMA process. Moreover, if the roots of the MA polynomial theta z are not on the unit circle, then theta tilde can be chosen such that the ARMA process with theta tilde as an MA polynomial to be invertible. What can we learn from this property? We can learn that any stationary ARMA process can be transformed into a causal process. This property is important since when we fit an ARMA process to a time series, we can assume fitting a causal process. Again, as we'll see in the next section, in the next lesson, we can derive the autocovariance function for an ARMA process using the invertibility property of the AR polynomial for a causal process, hence the applicability, the utility of this property. In summary, in this lesson, I introduced the definition, the concept of invertible and causal processes in the context of ARMA modeling. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on ARMA modeling, and in this lesson, I'll introduce the estimation of the autocovariance function, but also another dependence measure important for ARMA models, which is the partial autocorrelation function. I'll remind you once more the notation of an ARMA process with the AR and MA polynomials describing such a process. We have learned about the general definition of the autocovariance function. For stationary processes, the autocovariance function is very useful in describing the process. Here we'll learn about the property of the ACF for causal ARMA process. Specifically, if xt is a causal process with the representation as a linear process with psi j the coefficients of the linear process, the ACF is equal to sigma squared times the sum of all products between psi j and its lagged coefficient psi j plus h. That is the sum of the products of all combinations of the coefficients that are h lagged away from each other. However, in order to get the autocovariance function using this formula, we'll need to first derive the coefficients of the linear process, the psi coefficients. How to derive those coefficients? Recall that the relationship between the psi polynomial and the AR and MI polynomials of the ARMA causal process is as on the slide. We can start with this relationship, which can be rewritten as the product between psi z and phi z is equal to theta z. Expanding out of the polynomials on both sides and equating coefficients of z to the power of m for m equal to 0, 1, 2, 3, and so on, we get the system of linear equations where the psi's are unknowns. The system of equations is provided on the slide. Thus, deriving the psi coefficients reduces to simply solving a system of linear equations. For the estimation of the ACF, we can use the same approach as for any other stationary process. Specifically, we can use a sample autocovariance function. We estimate the sample autocorrelation by dividing the sample autocovariance by the estimated variance or the estimated covariance at lag 0. Correlation between two observations in a time series at two time points can result from a mutual linear dependence on observations at other time points called confounding. Another important measure of dependence for a time series that accounts for this confounding is the partial autocorrelation function, which gives the partial correlation of a time series with its own lagged values, controlling for or conditioning on the values of the time series at all shorter lags. In contrast, the autocorrelation function does not control for other lags. Here is the formal definition of the partial autocorrelation function, or abbreviated PACF. It is a function of the lag h. It is 1 at lag 0. For lags larger than 0, it is the last element of the vector alpha h obtained from multiplying the inverse of the matrix gamma H with the vector gamma H, where the matrix gamma H is a matrix of the autocovariance function at I minus j for all combinations of I and j, and the gamma H vector is a vector of the autocovariances at legs 1, 2, up to H. You probably recall to have seen the matrix gamma H and the vector gamma H before. They came up when I introduced prediction of linear processes. In fact, there is a direct relationship between PACF and prediction of a stationary time series. Assuming that the dependence reduces as we increase the lag, that the one lag linear prediction is a linear combination of the past observations of the time series. If we select the coefficients in this linear prediction by minimizing the mean squared error, then we obtain the so-called the best linear unbiased predictor, or BLUP. We define this prediction for linear process. We defined this prediction for linear processes in a previous lecture. Given this definition of BLUP, the partial autocorrelation is the coefficient AH in the best linear predictor as defined here on the slide. In order to estimate PACF, we can first estimate the autocovariance using the sample autocovariance function and plug in the estimated values in gamma H matrix and gamma H vector to obtain their estimates. Then we can use the formula for the PACF, but this time using the estimates as provided on the slide. The sample partial autocorrelation function and the sample autocorrelation function are important in identifying a good model for a given realization of a time series, as I will illustrate next. We consider now xt to be an MA model of order Q. That is, xt is equal to theta b times the white noise zt. An MA process is a causal process with a finite number of non-zero coefficients. Recall also the formula of the autocovariance function for a causal process provided on the slide. Now replacing the coefficients of the causal process with the coefficients of the MA process, it follows that the autocovariance function is 0 for all lags larger than Q. Thus, we can identify the lag of the MA process using the ACF plot. For an ARMA process, it can be shown that the PACF has the property that it is 0 for lags larger than the order P of the error process. Thus, we can identify the lag of the error process using the PACF plot. To summarize, if we have an error process, we can identify P using PACF, and if we have an MA process, we can identify Q using ACF. Unfortunately, there are no such simple rules for ARMA PQ processes in general. In summary, in this lesson, I introduced the derivation and estimation of two dependence measures that are important in ARMA modeling, particularly the autocovariance and the partial autocorrelation functions. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in Stewart School of Industrial System Engineering. This lecture is on ARMA modeling. And in this lesson, I will continue the introduction of the concepts of the ACF and PACF, the two autocorrelation functions, with a simulation study. This is a simulation from a previous lesson. In the simulation, I simulated MA processes as shown in the box in the right. The first process has coefficients 0.5 and 0.2, where the second process I've changed the coefficient from 0.5 to minus 0.5. The ACF plots are here. The upper plots are for the normal distribution and the bottom plots are for the exponential distribution. Across all ACF plots, we see one important common characteristic. All of them have the first two values of the ACF plot to be large outside of the confidence bands that are shown in blue, whereas for other lags, the sample autocorrelation is small, close to zero. Thus, these plots say that the sample autocorrelation is large for lag equal to 1, but approximately 0 for lags larger than 1. Note that we do not have the exact autocorrelation function, but an estimate of this function. Moreover, its estimate is not exact, but it's a random variable with a distribution, as I will explain in more detail in the next lesson. Because of this, we do not expect the sample autocorrelation to be exactly 0 for lags larger than the order of the MA process, but to be approximately 0. Thus, the ACF plot indicates that the order of the MA process is 1, which is the order of the process we actually simulated. This is another example I use for illustration of ARMA processes. For this example, while I simulated an MA process, the noise used to simulate the process is non-stationary. The process simulated in this example is in the box in the right. This is a time series plot and the ACF plot for this time series. The order of the simulated MA process is 3. From the ACF plot, we see that the sample autocorrelation function is large outside of the confidence band for the lags 1, 2, and 3, but close to 0 for lags larger than 3, indicating once more that the order of the MA process is equal to 3. Note that the property of the autocorrelation function is only for stationary processes, while in this case the simulated process is not stationary. However, even in this case, we find that the property of the autocorrelation function is maintained. This is an example of AR processes. For this example, I simulated AR processes with order 2. The coefficients of the first process are 0.8 and 0.2, whereas for the second process, the coefficients are 1.8 and minus 0.9. The simulated error processes are in the boxes in the right. The error polynomials of the simulated AR2 processes are quadratic polynomials. In order to evaluate whether the processes are stationary, we need to solve the equation of the error polynomial equated to 0. For the first process, one solution to this equation is equal to 1. Thus, this process is not stationary. For the second AR2 process, none of the zeros of the error polynomial are on the unit root circle. Thus, it is stationary. In this example, we are not going to look at the ACF plot, but at the PACF plot because of the property of the PACF for an AR process. The upper plots are the time series plots. From the time series plots, the first simulated AR2 process is clearly non-stationary, as we note an increasing trend over time. For the second simulated AR2 process, there is not a clear trend. However, we do distinguish some sort of pattern. The ACF plots are on the bottom. The PACF plots are similar to the ACF plots in that they are bar plots, with each bar corresponding to a lag. One difference is that the PACF plot begins with lag 1, not 0. The PACF plot of the non-stationary AR2 process shows a large value only for lag 1, where all others are small, close to 0. If we were to use the PACF plot to identify the lag of the AR process, we identify an AR process with order 1. However, the property of the PACF for an AR process does not hold for non-stationary processes, and thus we should not use the PACF plot to identify the order of this process. On the other hand, for the second AR2 process, the PACF plot clearly indicates an order 2 AR process. since the values of the PACF are large for lags 1 and 2. In order to simulate an ARMA process, I used a different R command, arima.sim, which allows simulation of ARMA processes. To use this command, if the white noise is Gaussian, then you do not need to specify it. Otherwise, you will need to specify through an option of the function called rand.gen. The important input of this command is the length of the process, here it is 500, and the AR and MA coefficients. The ARMA process generated here is in the box below. For this process, the orders are P equal to 2 and Q equal to 2, thus an ARMA 2-2 process. The AR coefficients are 0.88 and minus 0.49, and the MA coefficients are minus 0.23 and 0.25. I also specified a standard error for the white noise. The time series plot is here, along with the ACF and PACF plots on the bottom. The simulated ARMA process shows large volatility around the zero line, with some pattern but quite choppy. The ACF plot is on the left and the PACF plot is on the right on the bottom. The sample ACF is large for lags up to 4, and the sample PACF is large for lags up to 3. If we were to use this plot to identify the lags for the AR and MA in the simulated ARMA process, we would identify an ARMA process of orders P equal to 3 and Q equal to 4. However, the simulated ARMA has orders P equal to 2 and Q equal to 2, thus not correct. As I pointed out in the previous lesson, we cannot use the ACF and PACF plots to identify P and Q in an ARMA process. In summary, in this lesson, I illustrated the estimation of the autocovariance function and partial autocorrelation function using a simulation study of the AR and MA processes. Thank you.